Hello, my name is Jonathan Rivas. Today I'll be solving problem 3.43, part 8 only. The question reads, a conducting sphere of radius A at potential B naught is surrounded by a thin concentric spherical shell of radius B, over which someone has glued a surface charge sigma is equal to k cosine theta. Sigma is the function of theta, uh, and where k is a constant, and theta is the usual spherical coordinate. Part 8 wants us to find the potential at each region. The first region where R is greater than B. The second region where R is greater than A but less than that of B. Alright, so since the configuration is that of an azimuth symmetry, then we can write our potential as the summation of A sub L times R to the L plus B of L over R to the L plus 1 and P of L cosine theta, where this is your Lagrangian polynomial. Alright, so let's see. So when R is greater than B, we know that as the potential the potential is approaching 0 at infinity. So in that case, that means that A sub L is going to equal 0 for all of L, right? So that gets rid of the first term. So our potential ends up being the summation of just this second term of the Lagrangian polynomial. So B sub L over R of R to the L plus 1 in the Lagrangian. Alright, so for our second region, since this is kind of another region, I'm gonna use different coefficients in this region. This still applies, so we can say between A and B, our potential is going to be the summation of C of L sub L, R to the L, plus D sub L, R to the L plus 1, Lagrangian. Right. And then of course when R is less than A, then our potential is just going to be B naught. Alright, so we have this case here, this case. So we have 3 coefficients that we need to figure out along with V naught. So we have to consider the following boundary conditions here. Let's see. So we have 2 boundary conditions that are pretty much the same. One of them is going to be that V is continuous at A, and then it's also continuous at B. And then for the third boundary condition, if we were to differentiate the potential to respect to R, right, delta, we'll find that we'll have sigma theta, or glued charge, over epsilon naught at B. Alright, so let's work through these boundary conditions and let's see how I'm doing. Work through them and figure out these coefficients. So I'll turn over the page here. Alright, let's start with the second one. Alright, so by working through the second boundary condition, since B is continuous at B, I can set this equation here. It's at R is going to equal to B, so it's going to equal to, let's see, C sub L, B sub L plus 1 PL cosine of theta. So I was able to do this because our second boundary tells us that the potential is continuous at B, and you know this was the case where R is greater than B, and this was the case where R is less than B. So we just set them equal to each other. That kind of, we could neglect the boundary. I mean the summations for this case. We'll just have B sub L B L plus 1 and equal to, don't neglect that, B sub L plus D sub L over B plus 1. And these cancel as well. So we can solve for B, right? B sub L. And we're going to find that B sub L is going to be lowercase b 2 L plus 1, B to the 2L plus 1, C of L plus D of L. So that's one of them. If we consider the first condition, then we can use summation of C sub L of A to the L plus D of L over A to the L plus 1 polynomial. And this is going to equal to two cases, right? It's going to be our V sub naught, where if L does not equal 0, then we're going to have a case like this, right? A sub L plus 1 is equal to 0. This is if L does not equal to 0. But if L does equal to 0, then we're going to have this case, right? And just evaluate this 1. It's going to equal to our V sub naught. This is for when L does equal to 0. So to consider these two cases and solve for D of L and D naught, D of L. Alright, so if we plug in, putting this, right, this should be our second one, plug this into 1, then that gives us that B sub L equal to lowercase b to the 2L plus 1, C of L minus A to the 2L plus 1, C of L, and that's if L is not equal to 0, and when L does equal to 0, then we'll have another term, we'll call that B naught, B C sub C naught, right, plus A V naught minus A C naught. Therefore, if we simplify this, we'll have B sub L is equal to lowercase b to the 2L plus 1 minus A to the 2L plus 1 times C of L. This is when C is not equal to 0. B naught is equal to B minus A. C naught plus A V naught. Right? So I'll call this one, let's say 1 prime, because we're going to have to plug this in a little later. Let's see. Now we have to apply our third boundary. Let's see. This can be the case when R is L plus 1. So for third case here, it's going to be our summation. We can neglect the first term. We're going to be just left with B sub L of negative, let's see, yeah, L plus 1, right? Alright, radius is still going to be that of B of L plus 2, 1, Lagrangian. Again, remember this is for our third boundary condition. It'll be minus the summation, let's see, CL of L to the B, L minus 1 plus D sub L. Let's see, minus L plus 1, B sub L plus 2. Right, this goes like that, and this will be equal to our negative K epsilon naught P sub L. Again, just refer what I did with that. What did I do with this? Oh, sorry, the same one. Yeah, refer to this third boundary condition, that if you're confused on what I'm doing. Remember, I'm taking the derivative of our potential to respect of R. That gave us our sigma over epsilon naught. This was at B. So that's how I got that. Okay. Again, if in this case it'll be whether L equals 1 or not. So if L does not equal 1, then we'll have, let's see, it'll be negative L plus 1 over B to the L plus 2 BL minus C of L B L minus 1 plus D of L negative L plus 1 B to the L plus 2, and this will equal to 0 if L does not equal 1. If let's see, we can simplify this a little bit more. Sorry, negative L plus 1 B sub L minus L C L B to the 2L plus 1, that's, yeah, plus L plus 1 D sub L is equal to 0. Yeah, and I guess I could move that over there. I'll end up with L plus 1 B sub L minus D sub L. I can move that guy over there. Minus L B to L plus 1 C sub L, right? So, this is B. Okay, let's continue this. And then we're considering for when L does equal to 1, then we'll just have B sub 1, that'll be 2, over B sub 2 plus C1 plus D1, negative 2 over B2, right? And this is going to equal to K epsilon naught. And this is for if, no, this is for when L equals 1, yes? Then I guess we can solve for, not solve for K. We can simplify this, right, a little more. C1 plus 2 to the B third, B to the power 2 over B to the power 3, B1 plus minus D1 is equal to K. Right? We put everything together, then you'll have L plus 1 B sub L minus D sub L plus L to the B to the 2L plus 1 CL equals 0. This is what's the case when L does not equal to 1. And then we have our case when L does equal to 1. Then we have C1 plus 2 over B to the third, B1 minus D1. That's equal to K over epsilon naught. Alright. I'll call this 3. Now, there's going to be a lot of arithmetic now, a lot of plugging in. If we plug in, what do I do with you? 2 into our 1 prime. If we plug 2 and 1 prime into 3, then we'll be able to figure out all of our coefficients, and then we'll plug those coefficients back in, and we'll be able to find our potential in these given regions. So let's work through that. Okay, so 2 and 1 prime into 3, which is this guy. Sorry. All right. So I guess for the case for when L is not equal to 0, or if I guess L is not equal to 1, we'll have L plus 1 times, let's see, B to the 2L plus 1 minus A to the 2L, plus 1. This will be C of L plus A 2L plus 1 C of L plus LB to the 2L plus 1 times CL. This will equal to 0. Let's see. Simplify this a little bit more. It'll be L plus 1. Let's see. B of 2L plus 1 C of L plus LB 2L plus 1 CL is going to equal to 0. Okay, so let's see. We can simplify this a bit more. We're going to end up, if you can simplify it down to 2L plus 1, and just going to multiply by CL equals 0. Just divide that. So CL is just going to be 0. Okay. And I guess that's kind of obvious now, since we have just this coefficient equal to 0. We could have seen from the get-go that CL is going to equal to 0. Alright. Let's see. Now, if we can plug in 1 prime into 2 to figure out C1 and D1 and B1, I guess. Let me flip this. Okay, so this, let's see, then the 1 prime. Oh, actually, yeah. So 1 prime and 2 then, because we have CL equals 0, then BL has to equal to CL, which has to equal to DL, which equals to 1, which equals to 0. And this has to be for when L is greater than 1, right? Okay. Yeah. Yeah, because we have this coefficient goes to 0. It's equal to 0, rather. We plug that back into 2. Yeah, that's going to equal to 0. That's going to go to 0. And that's going to go to 0. Yeah, okay. Because these coefficients are dependent on CL. CL is equal to 0, so then BL is going to equal to CL, that's going to equal to DL, and that's going to equal to 0. Alright. Now for when L is equal to 1, I'm going to have C1 plus 2 over B to the third. B to the third minus A to the third. C1 plus A to the power 3, 1. Alright, just equal to K. Through some algebra and arithmetic, we can boil this down to it's C1 plus 2C1 is equal to K. Divide that to that side, multiply that through, divide that. Yeah, okay. No. Yeah, no. Yeah, it should be. Once you work through the arithmetic of this, you'll end up with C1 plus 2C equals K. So then C1 has to equal to K over 3 epsilon naught. So then D1 is equal to A to the third C1. So that means that D1 have to equal to negative A to the third K over 3 epsilon. Right. That's that. That's that. And B1 is equal to B to the third minus A to the third C1. So that means B1 has to equal to B to the third minus A to the third power 3. I keep saying third, I'm so sorry. K over 3 epsilon naught. Alright, let's see. Now, final case of when L is equal to 0, then B is 0 minus D is 0 have to equal to 0. Yes? So B is 0 have to equal to D is 0. Then we plug that in. We have B minus A is C sub 0 plus A V sub 0 is equal to A V sub 0 A C naught. So let's see. So BC naught is equal to 0. So C of 0 is equal to 0. D sub naught will have to we've stated that it's equal to B sub naught, so that has to equal to A V sub naught. Nice. So we found all of our coefficients. Let's see, did I have more here? No. Okay. So for the region of R is greater than B, greater than or equal to B, our potential in this case is going to be A times V naught over R plus B power 3 minus A to the power 3 K over 3R squared epsilon naught cosine theta, and then when r is, well, a is less than or equal to r less than or equal to b, our potential is then even now r plus k to the over the 3 epsilon naught. That's going to be multiplied by r minus h to the third, r to the second, cosine theta. Alright, and this will be our potential for those two regions. Alright, my name is Jonathan Rivas. Thank you so much for watching.